All right, welcome to the solution for practice problem number 1 in homework 6. All right, so let's talk about the knowns of the problem. So we know that we have a high temperature reservoir at 1960 degrees Celsius. We know that we have a low temperature reservoir at 20 degrees Celsius. Converting into Kelvin, these are 2233 Kelvin and 293 Kelvin. Okay, between these we actually have a combined cycle power plant, which means we have two heat engines. The first one is a Brayton cycle, and we put then some QH, we'll call it QHB, into that Brayton cycle, and then reject some amount of heat, we'll call that QLB, and then out of that heat engine we get some amount of work, which we'll call work out B. Now in a combined cycle, the heat rejected from the Brayton cycle is also the heat put in to the next cycle, a Rankine cycle. Brayton cycle is like imagine a large jet engine strapped to the ground, and you just pump a ton of air through this thing with a lot of fuel, and you turn a big shaft which turns a large generator. The heat rejected from that turbine then goes into the Rankine cycle, which is just a standard coal power plant. But in this case, we don't burn coal. We just use the rejected heat from the Brayton cycle to evaporate the water in the boiler. And so that Rankine cycle then rejects its excess heat, which we'll call QLR, to the cold temperature reservoir. And that is our true waste heat for the entire system. And we get some work out from this Rankine cycle. Okay, now we know the efficiencies of each individual cycle. The Brayton cycle has an efficiency of 40%. The Rankine cycle has an efficiency of 35%. All right, we also know the amount of heat we are putting into the system in general. So we know that QHB is 5 megawatts, the amount of heat we're putting into the first cycle, the Brayton cycle, or the hot high temperature cycle. We're asked to find first QH, QL, and the work out for each cycle. So that would be 6 things total, right? QH, B, QLB, workout B, QHR, QLR, and workout R. We're also asked to find the total workout for our entire power plant operating between these two temperature reservoirs, and the total efficiency of our power plant. All right, we'll move to the next page for our analysis. Okay, we'll begin with part A, where we want to find QH, QL, and work out for each cycle. Okay, and we'll begin with the Brayton cycle. Well, luckily, we already know QHB, right? That was a given right here. So QHB is 5 megawatts. This we already know. That wasn't too hard, right? Okay, now we will do an energy balance on the Brayton cycle. So going back, we're going to draw a box. It will be a red box around the Brayton cycle. And we're going to do an energy balance where we have Q in QHB is equal to the workout plus QLB. So doing that, we say, still in red. So the work in is equal to the work out. Okay, so in is QHB, and out is QLB plus work out B. I'm not using dots above these, but these are rates. Okay, So we also know that the efficiency of the Brayton cycle is 40%, right? That was one of our knowns. And we can define the efficiency as what we want over what we have to put in. From a heat engine, we want work. It is an engine. We're trying to do work. And in the denominator, we put what we have to put in. To get that work, we have to put in heat. It is a heat engine. Okay, so we can use this equation and this equation in order to solve for both this and this. We'll begin with the efficiency equation, right? The efficiency of our Brayton cycle, which is 40%, is equal to work out divided by QHB. Well, we can rearrange this to get the work out of the Brayton cycle is equal to 40% of the heat input, which is 5 megawatts. And so when we do that calculation, we get 2 megawatts. Okay, now we can plug this into our energy balance equation and get QHB, which is 5 megawatts, is equal to QLB, which is what we're looking for, plus the work out, which is 2 megawatts. So if we put in 5 megawatts, we got out 2 megawatts of work, then the heat rejected must be what's left over, or, 3 megawatts. Okay, that was the Brayton cycle. Now let's do the Rankine cycle. You know what, actually, we're going to, since I accidentally skipped a slide, we're going to do that right here, so we don't run out of slides. Okay, so for the Rankine cycle, we're going to do a new energy balance. And this time, we're going to do that energy balance in blue. So we're going to put a box around the Rankine cycle, and we're going to balance the energy going in and the energy going out. We're working in rates, so energy per unit time. Okay. Now, first, what we already know is that Q rejected from the Brayton cycle is equal to what is brought into the Rankine cycle. Right? This is kind of the definition of a combined cycle plant. And we're going to need that in order to solve this problem. But yeah, so going back to our energy balance, what's going in is QHR, which is again equivalent to QLB. And that's going to be equal to the work out of the Rankine cycle plus the heat rejected from our Rankine cycle. Also, just like before, we're going to define the efficiency of our Rankine cycle, which is 35%, as the work out from our Rankine cycle divided by the amount of heat we put into the Rankine cycle. All right, we're going to start with this efficiency equation since we already know this term, right? Because we know QLB, which is equal to QHR. So we're going to say the work out of our Rankine cycle is equal to 35% of the amount of heat we put in, which we find is 3 megawatts. That's the heat rejected from the Brayton cycle, which is what we put into the Rankine cycle. Rankine, it's like a celebrity name, you know, it's the Rankine cycle. Anyway, so 3 megawatts. And so 35% of 3 megawatts is 1.05 megawatts. That's how much power we're getting out. Okay, now we plug into our energy balance because now we know work out and we already knew QHR. So we plug in QHR, which was 3 megawatts. We got out 1.05 megawatts, leaving just QLR. We can rearrange to find what QLR is, and that's going to be 1.95 megawatts. All right, so those are our 2 cycles. Now we're asked for part B to find the total work out. To do this, we're going to draw another control volume. We're going to draw a green one, and we're going to draw it around both cycles. Both cycles would be our entire power plant. So what is the total work out of our entire power plant? Well, as we see from our control volume, that would just be the work out from the Rankine cycle plus the work out from the Brayton cycle. So let's add both of those up. We have work out from the Rankine cycle was 1.05 megawatts. Work out from the Brayton cycle was 2 megawatts. So 1.05 plus 2 is equal to 3.05 megawatts. Total workout, which means we are now ready to find the total efficiency. Let's go back to our energy balance. Remember, efficiency is equal to what you want divided by what you have to put in, or what you need. Well, what we need to put in is Q. Imagine now, instead of 2 cycles, we just have one big circle, right? We're putting Q in, we're getting work out. But that would be the total work total, both of these added together. So our efficiency is just going to be equal to what we want, our total work out, divided by what we have to put in, or our total. I'm sorry, not our total, but you saw from our box what we had to put in was the Q into the Brayton cycle. And you say, well, what about the Q into the Rankine cycle, right? Well, it's inside of our green box. See how it doesn't cross the boundary? This isn't heat we added to our entire system. This was just excess heat from the Brayton cycle that we were able to use to run another cycle entirely. And that's why combined cycle is more efficient. One of our heat engines, in a way, operates for free, and that we're not adding new heat, we're just using rejected heat as new heat. So looking at the total amount of energy crossing the boundary, we have work going out, and the energy coming in is just QH into the Brayton cycle, crossing our green boundary. So that would be 3.05 megawatts divided by 5 megawatts is 0.61, or 61%. So you see that our combined cycle, our total efficiency is 61%, which you'll notice is not as much as if we'd added these two efficiencies together. But what we really got out of this, right, was if we operated one of these by itself, we would get these efficiencies. By operating them on top of each other, by letting the Brayton cycle reject heat into the Rankine cycle and reusing that otherwise rejected heat, we achieved a total efficiency of 61%. This is why a combined cycle plant is the best if you are burning a fossil fuel. Okay, that's our answer. Thanks for watching.